So now comes the exciting part of the course. Well, the most exciting part. This table that you see in front of you just took me 3 years to make. It is very strange that the way most textbooks approach statistical mechanics is very different. So I talked to maybe like 10 physicists in the course of trying to make this one table. So this is a very, very important table. We will, over the course of the next 3 or 4 weeks, try to figure out all of those words that this table says. So we're going to start talking about every single one of these words that are in there. So for example, right now, none of them should make sense to you, except for people who may have taken quantum. You may have heard Maxwell-Boltzmann or quantum fluids or something like this, but I'm pretty sure you have not heard canonical or grand canonical. Try to be patient. Statistical mechanics is one of the most difficult things to learn in physics, except for quantum mechanics, probably. I am going to try to make it as easy as possible. However, even saying that, there is going to be things that you have to be patient with me with, okay? So full attention to be paid from this day forward until the end of the semester. Got it? Okay. So today we are going to start talking about these things. We will see how far we get. So I'm going to start talking about section 1.1, which talks about there are the different kinds of mechanics that we have. So let's start. What do we know? We know that throughout history, we've had classical mechanics. Classical mechanics is F equals ma. It is an experimental science, and it doesn't, how do I say this? So classical mechanics has classical thermodynamics, which is based on our experimental laws. Remember Boyle's law, Charles' law, all of those laws that we had? However, that makes no explanation about the nature of matter. Because it doesn't tell us about the nature of matter, another field was developed in around mid-19th century called molecular theory of gases. Now, it may seem like it's not a big deal to us right now, but it was a huge deal because people did not actually believe in the concept of particles. So molecular theory was the first theory that treated this continuous solid table as being made up of discrete particles that they called molecules. So in the molecular theory of gases, they said that matter is not continuous, but rather made of particles which are discrete, and they called them molecules. Now imagine this is a very strange concept at that time, because as you can see, look at the table in front of you. It looks continuous. Look at anything around you. They all look continuous. But now these people are saying that instead of this continuous thing that we see, actually they are made up of tiny, tiny molecules that are combined together, and those tiny particles are called molecules. So they based the nature of matter on the definition of these molecules. So the theory that was developed was called the molecular theory. And that molecular theory gave rise to two distinct individual theories called kinetic theory of matter and the other one was called statistical thermodynamics. So the molecular theory was differentiated as kinetic theory and statistical thermodynamics. So kinetic theory is also called the dynamic theory, and it says that all matter consists of tiny particles which are physically spaced away from each other and have gaps in between. Okay, so this theory takes into account that there are particles with gaps in between them. So for solids, these particles are stuck in place, whereas for fluids, which include both gases and liquids, they can be moving. Okay, so these particles in solids are stuck in place, whereas for fluids, they are allowed to move about. So fluids, when they include gases and when they include liquids. So when they include gases, they're both in random state of motion, but the distance between them is far. When they are fluids, the distance between them is kind of close and they're kind of stuck together. The other theory that was developed was called statistical thermodynamics. In the statistical thermodynamic system, the actual theory says that we ignore all of the details of the particles themselves, but instead we talk about what I'm going to be referring them to as ensembles, like a collection of particles. So the molecules make up certain ensembles, assemblies. And we address the collection of molecules instead of each individual molecule in a substance. So far, so good? Okay. So what happened next? So both the kinetic and the statistical thermodynamics assumed that classical mechanical laws could be applied to all particles all the time without any modification. However, experimentally, we found that that was not true. So classical laws that were applied to large scale systems, like for example, for our moving cars, for humans, for planets, they failed when we were talking about tiny molecules, which led to the development of the quantum theory that is individual in itself and distinct from classical mechanics, which led to quantum mechanics. So now the field of mechanics needed to be modified. Okay. Do I need to write all of that down, or are we good with my explanation?
Yes, write it down.
Okay. So how do I say this? Initially, scientists believed that all classical laws could be applied to both kinetic and statistical thermodynamics without any modification. But experiments did not give us the correct results. So modifications needed to be applied for small scale systems. Which led to the development of quantum mechanics. Which means that now we have two major types of mechanics: classical and quantum.